Hi, everyone. I'm Duan. I would like to thank the organizers for this chance to tell you about the application of fluorine solid-state NMR for PET tracer binding and protein structure assignments. Okay, something's wrong. Okay. First, let me talk about the PET imaging tracer for Alzheimer's disease, or AD. So AD causes severe cognitive and functional impairment, and currently it's the 6th leading cause of death in the US. And unfortunately, so far there's no cure for AD, but there are 2 biological hallmarks for a potential early detection. One of them is the plaques formed by the A-beta peptide. The positron emission tomography is an emerging modality for AD diagnosis, which requires very special radioactive imaging agents to function. And fluoromethanol is one of the FDA-approved A-beta specific PET ligands, which is derived from seroflavin T. We want to ask, what is the binding site and bond structure of the fluoromethanol in A-beta? And our approach is the fluorine solid-state NMR distance measurement in the carbon 13 labeled A-beta. So to get our A-beta fibrils, we collaborate with Dr. Haifang Wu's labs in Wichita State University. The recombinant A-beta peptide is sequentially it's monomerized by sequential dissolution in HFIP and DMSO, and then fibrillized for 3 days. The resulting fibril is very homogeneous under transmission electron microscopy. Okay, to bind the poorly soluble PET agent to the fibril, we have to adopt a method modified Mu et al. Thankfully, at the same time we start the project, in which the BSA facilitates the binding. So in short, is we co-solubilize the PET ligand and BSA in 25% DMSO, and then dialyze it to remove the DMSO. And then the PET solution is titrated against preformed fibrils. So based on the titration, we find the binding saturate about 20% more A-beta, and among which about half is tightly bound. Later, we collect 1D carbon and nitrogen CP spectrum and found that the APO and PET bond sample are almost identical. In fact, the nitrogen and carbon sequential assignment based on 2D and 3D experiment show no evidence of chemical shape perturbation. Next, we collect fluorine 1D spectrum from the PET bond sample to investigate the bond ligand. The rigid protein selected by CP shows chemical shift anisotropy set by PET matching the pure powder form, meaning that they are very rigid. And quantification based on the spectral integral indicates a 1 to 10 PET tracer to A-beta binding stoichiometry, matching exactly to the biochemistry result. And interestingly, a second sharper component with smaller CSA shows up in the quantitative DP spectrum, which can be assigned to the loosely bound fraction that we also find in the biochemistry assay. Then we applied fluorine readol rotation echo the double resonance experiment to detect the peptide residue close to the fluorine in the PET tracer, which should reveal the binding sites. Due to the low sensitivity of the CF readol, we actually developed and applied a carbon-detected HF readol to this system. And the carbon-detected HF readol has achieved the broadband spectrum and high readol efficiency at the same time. So unfortunately, the resolution in the 1D is not adequate. So we collected a 2D C-series of HF readol. The readol difference shown in red, and the control spectrum is overlaid in blue. And there's many cross-peak in the aliphatic region, and among which the strongest one can be assigned to H14, valine 12, valine 18, valine 39, and valine 40. While in the aromatic region, the difference peak in the diagonal can be assigned to histidine 13 or 14 and phenylalanine 19 and 20. Taken together, the HF reader reveals the PET ligands most likely binds at the double histidine motif, double valine motif, and double phenylalanine motif, and the double valine motif at the C terminal. So to investigate if the residue identified by reader are energetically favorable for binding the ligands, we applied molecular docking of the PET ligand to existing A-beta fibrils models in HEDOC. In one of the in vitro A-beta model, the PET ligand binds exclusively parallel to the fibril axis and straddling about 3.5 beta sheet strands. The aromatic planes form various angles with the local beta sheets planes and apparently stabilized by either CH pi or CH pi or pi interactions. Interestingly, similar binding sites and poses are absorbed on a model derived from meningeal fibrils extracted from AD brain. So we hypothesized that the unique double histidine, double phenylalanine, and double valine motif ensures the consensus binding sites, no matter what the exact arrangement of the side chains. Okay, so next, let's move to a second project. So fluorine reader is powerful for looking at the small molecule binding to protein or the protein structure assignments. However, it can be challenging to be applied to system with more than one fluorine signal, and it's actually quite common to have multiple fluorine signal in the system. For example, even when we have only one fluorine site, like the fluoromethanol, we can have more than one fluorine signal due to different chemical environment. And it's even more common to see multiple fluorine sites in either the ligands or in the protein. So to solve this, the traditional approach is either specific mutagenesis or single site labeled peptide synthesis, and they are very time consuming. So the other approach is relying on the fluorine X chemical shift correlation. And so far, 2D approach and 3D HH and FFH approach has been tested and applied in real world system. However, 3D FXH hasn't been reported, and is very desirable for optimal sensitivity and resolution. So here we explore FNH. So we implement several 3D correlation experiments that involve F and H, and tested on CDN GB1 example, either fluorine labeled as tryptophan or phenylalanine. In the end, we find that the experiment to use out and back reader to correlate fluorine and proton, and then use CpHNH to transfer the fluorine chemical shift encoded proton polarization to nitrogen, and then back to proton for detection to be the best method. So therefore, we name it as an out and back reader CpFNH experiment. The phase cycling for the experiment is shown here, and later I will want to briefly describe it. Okay, so comparing with HNH resolved HF reader, the 2D version of the FNH experiment shows the exact same spectral pattern and pretty high efficiency. And in the 3D version, the fluorine dimension separates the two fluorine signals. And based on the correlation and the GB1 crystalline structure, we can assign the fluorine at -101 ppm to the phenylalanine 13 site, while the fluorine at -109 ppm to the phenylalanine 52 site. Next, we apply FNH to TPP bound with EMRE, a system that our group has previously investigated. Previously, HF reader helped us identify the binding pockets, but cannot distinguish the 4 fluorine sites, which sit in different chemical environment and have different fluorine chemical shift. For example, one of them is at -97 ppm, one of them at -99 ppm, and the overlapping sites at -101 ppm. Here we use 3D FNH to identify that one of the binding site at -97 ppm is closer to E14A sites and etc. Other one at -99 ppm is most likely close to Y60A and etc. So comparing with the comparing with our structural model, we can distinguish this site based on their distance to the neighboring residue. So I hope I demonstrate the power of fluorine NMR for PET tracer binding and protein structure assignments. And I want to thank everyone in Hong's group, especially Professor Hong, Kelly, Aurelio, Harrison, and Alex for support and discussion. And I also want to thank Professor Haifeng Wu's lab in Wichita University for providing the A-beta Fabry examples. Next, it's the end of the slides, and I think we can start with the discussion.